So as far as the project is concerned, I rearranged a few things. I'm hoping by tonight you will have selected a topic or decided if you have a database that you want me to review to see if it's suitable for the topic, for the project or database on your own. And I've already had a couple of people contact me about that. But you can go ahead and it would be best to select a topic now so that you can go ahead and start working on it. Don't get too bound up on it because it really doesn't matter that much. Most of these databases, all of these topics involve similar kinds of data, and you'll be doing the same operations. It's just a question of what you think might interest you the most. Okay, but I don't think you'll be at an advantage or disadvantage by choosing any of the three suggested topics. Okay, if you have your own topic, like I said, we should review it a little bit just to make sure that we're on track with it. Okay, so by tonight, I'm hoping all of you will have selected your topic. By 7/18, which is 5 days from now, which I guess is Monday, right? I'd like you to upload the first part of your work on the project. And that's going to include basically an introduction to what the issue is or problem that you're examining it. In other words, you're looking at maybe flu shots and why that's of interest and why you're interested in whether insured people, whether having insurance will affect whether or not you get a flu shot, and give me just like a break what you think, what your approach to this is, and why this might be of interest, or why it might be of value. Okay, then do your descriptive statistics. Put them on a Word document along with your descriptive introduction to the problem, and tell me about the well, first of all, the demographics of your sample. And who is that? That's New York City. That's people in New York City. If you're focusing on men, then tell me about the men, the age ranges, the maybe what percentage of the population is men. Maybe there's some information about other characteristic information about the population that do you think may be relevant to whether or not they might get a flu shot, diabetes, so on and so forth. Okay. Then also give me relevant descriptive statistics for the variables that you're looking at. So for instance, one of the variables obviously is going to be, did they get a flu shot or didn't they give a flu shot? So you might present that as a table. You might present that as a pie chart or a bar graph or something like that. What percentage of people got a flu shot, which didn't get a flu shot, which groups of people tended to get more flu shots, and so on and so forth. So the descriptive statistics, what you might also include in there, if you've started on it, a little bit of research about flu shots. Are they effective, not effective? How many, whether or not, whether certain years when they're recommended, what a flu shot is, so on and so forth. Just a little bit of background information on the topic that you're examining. Okay, and it would be nice if you had a couple of references, technical references. Not like, as we were talking, not the Daily News, but something that would be a paper that you came across that had something to do with flu shots and whether or not people were getting them and whether they were effective. That's just an example. You might choose a different topic. Okay, so those two things, if you could upload them, there's a section there on Blackboard now where you can upload it as an assignment with the graphs and everything else and tables. If you could upload them by Monday, it'll give me a chance to review them. And if and when I mean review, I mean, with 25 of us or whatever, I'm only going to be able to take a quick look at them. But at least I'll be able to see, what you've got, and if I think you need, I need to fill in some information or take a different approach or something like that. So that'll give me a chance to look at it. Then by either, let's see, okay, by the 22nd or the 25th, depending on when you're going to do your presentation. I'm going to put a list up where you can choose to do your presentation either on Monday or Wednesday, the 25th or the 27th. If you're going to do it on the 25th, then by the 22nd, I'd like you to upload your analyses, your associations, and basically an outline of your summary and conclusions. Doesn't have to be your final project, but just what you think that you're going to be presenting roughly. Okay, and then by the date that your presentation is due, upload, the third upload will be the entire presentation together. Okay, so that everything's in one shot, so I'll have something I can grade. So the only one of those things that I'll actually be grading is the final presentation. Okay, so what basically that means is that I'll have even though there's no, there are due dates on this thing that I put in here, but they're not graded. So the real purpose of this is for me to give you some feedback while you're in the process. So if you neglect to do it on time, it's not a big deal as far as I'm concerned, but it'll be better if I get a chance to help you out if I can on some of these things. Okay, so you'll be graded mostly on the material that you create and a little bit on the presentation. I haven't really decided on a percentage either way, but it'll be mostly on the actual upload that you wind up giving me. Okay, you can always help yourself out a little bit on the presentation, but I don't want to make this a acting class. It's not an acting class. So if you're not the best presenter in the world, you won't be disadvantaged. Okay, so now your presentation is going to look like a poster that would be presented in at a conference or something like that. Okay, we're going to have regular poster board. I think it's usually roughly about 30 inches by about 36 inches or something like that, vertically or horizontally. And you'll print out individual pages. We want you to use big type. We don't need a lot of words. We want you to use relatively large type, so if someone's standing in front of it from a few feet away, they can read your description, your introduction, your descriptive statistics, your presentation. And just to help you out kind of on what some of the others look like, here's a few that some other students did from last either last semester or the semester before. Some of them were more theatrical than others, but you get an idea. You can see that, and these would this one is kind of like has a bit more material than most, but you can see a lot of it was punctuated by graphics, by tables, and so on and so forth. So we're not looking for a giant exposition of words here. We're looking for more an understanding of what the topic is, how to use the statistics. Okay, and I will present you. I'm gonna throw a little bit of a curveball at you now, because what I did was I just uploaded the community health data set from 2014. The people that did I have a few presentations from previous semesters, some good ones that if you use the data set from 2014 instead of 2011. That I'm willing to upload so you can see what other people have done. Don't copy their work. Don't imitate them. Do your own work and stuff like that, but at least you'll have some sort of background on, what those others look like, other than just that picture from a distance. But you're going to have to, if you're going to do that, you're going to have to use the data set from 2014 instead of 2011. Matter of fact, I'll probably have to tonight, unless somebody really squawks, I'm going to remove the data set from 2011. So now I just want to show you what those data sets look like now, so you can kind of be prepared for this whole thing. In fact, maybe I'll do like a little bit of a quick analysis, as a matter of fact. Okay, I'm going to get these out of the way. Have a whole bunch more pictures. Okay, let's see. Let me open this up. So this is New York City Community Health Survey from 2014. Okay, now when I open this up, this has been translated from another database called SAS. Okay, and so part of the database does not carry over certain coding, and we'll see that in a second. Okay, that's displaying behind me now, right? Yes, it is. If you want to turn the light off, if it's easier, or you can leave it on. Either way, that's up to you guys. If it makes it easier to read the board. Okay, there you go. All right, so we can see in the data view, we see a lot of numbers. Not very descriptive, is it? Unfortunately, those numbers are not coded in this version. See, when I turn on value labels, turn them off, they stay numbers. The various parts of this are coded. I'm going to go to the variable view. And in the variable view, we can see all of the various, all of the variables, and almost all of them are the same as the variables that were in previous surveys. I think this one actually has a few more variables than the 2011 one does. But one of the reasons they do the community health survey is they want to look for trends. So it's in their interest to use the same variables year to year. So we can see that many of them, the names are fairly descriptive. For instance, if I go back up here, we may see, let's see, ever asthma. We know that probably, did I lose that somewhere? Here it is. This variable is ever asthma. We can guess that that's a survey question where they're asking, have you ever been told that you have asthma, or have you ever been diagnosed with asthma? And in fact, the question is actually available here. Okay, if you clicked in here to the whole line, it winds up stretching out everything. So I just want to click in there and drag it out. Have you ever been told by a doctor, nurse, or the health profession that you had asthma? Now, the answers to that question are coded as 1, 2, 3, so on and so forth. So we need to know what those numbers represent. Since you're only going to be using 2 or 3 of these variables, it's not going to be a big deal for you to code these. So there is a code book that goes along with these things. And here is the 2014 code book. And that was line number 39. Okay, and if we go through this, we can actually find, I went too far. We can actually see these various questions. I'm going to actually just do a quick search here for ever asthma. Okay, ever. Did I make a mistake there? Physical activity, nutrition. Not sure why it didn't come up with that particular word. Maybe I put in the phrase, have you ever been told? Okay, and let's see. This one is health issues. Last time you had blood pressure, blah, blah, blah. Have you ever been told that you need to take medicine for high blood pressure, medication? Let's get to asthma here. That high blood pressure, cholesterol. Have you been told diabetes? There you go. Question 4.2, as it's posed in the question list. There's another list of questions here. Have you ever been told by a doctor or nurse or the health professional that you have asthma? 1 is yes, 2 is no, 7 is don't know or not sure, and 9 is refuse to answer. Okay, so we know now we can go back and code this. Okay, let's go in here. So we can code this with the value 1 means yes. The value 2 means no. Okay, and we're not so worried about the rest of them for right now because we're going to ignore that data anyway. I'm going to click OK. So now if I go back to my data view, if I go to that variable, if I can find it, I'm going to change the view to value labels are on. So we should see it pretty quickly because it's going to be the only one with yeses and nos. There we go. And there's our variable there. Now, dirty little secret, once you've decided on what variables that you want to use, you can go here, and I'm going to go all the way back to the beginning here, hold down the shift key so that they're all selected, and I can tell SPSS that I want to clear all of those. I want to delete all of those. So you can just get rid of all the variables you're not going to use. So if I wanted to know a little bit about how many people, just descriptive statistics, how many people have been told they have asthma, how many people haven't been told they have asthma, I can go up to Analyze, Descriptive Statistics, and I'm going to go into Descriptives for starters. And I'm going to look for, here we are, the first one is ever been told, because we moved it. And I'm going to click OK. Okay, let's see. I didn't, data set uncoded. 1, 2, maximum 2. I don't think it did hang on, let me try that again. Descriptives, let me try frequencies. Frequencies, ever been told you have asthma? I'm going to click OK. And yeah, we got it that time. Okay, so actually it was trying to do what it shouldn't do because it's a nominal variable. It kept me from doing it. So SPSS did the right thing. So 1,100 people have been told that they have asthma. 200 people haven't been told they have asthma. So the prevalence of asthma in this population is 12.9%. Okay, now we may want to, we have a total percentage of 99.8% because 2% of the responses are missing. 21 people either refused or didn't tell or didn't know if they've ever been told. For one reason or other, they didn't wind up answering. So there's going to be ways for us to deal with that. So we can actually do a graph based on that. We can either go to analyze and the descriptive statistic frequencies, and we can ask it to produce a chart for us, a bar chart, for instance. Okay, do the same analysis again, except this time we have a look at relatively how many people in this population have been diagnosed with asthma. Well, how about men and women? Analyze descriptive statistics frequencies. Well, hang on a second. Let me do this another way here. Well, I don't want to get too far into this right now. Rather than wind up doing all of this right now, we also may want to have information, general information about the population, the age groups, how the age is distributed, what the mean age is, for instance. And then we might want to know whether the mean age for people that are diagnosed with asthma is different than the mean age for people who are not diagnosed with asthma. Well, let's see what we have in the way of age here. Okay. See if I can search on age here. Okay. Oops, what is your age? I think we actually have a numerical variable for age. Did I see it? Are you 18 years old or older? Maybe I'll try it this way. What is your age? You saw insurance go by there. What is your age? Question 8.1. Okay, so that's pretty far down there. Okay, and that's in demographics. So let's see if I can't find, what is the variable name there? The variable name is, let's see, I don't see it in here. Okay, way over in demographics. Let me go back to the variable view. And we'll get eventually down here, we'll get to some demographics. We should be able to see it. See, we lost some variables because I cut them off, but I think it's at the end, so I didn't lose that one, I don't think. Okay, age. Well, let's look. It's a scalar variable. Number of days consumed at least one alcoholic drink. Average number of alcoholic drinks. Age is going to be a scalar variable if we have it that way. Total minutes. Number of sodas. Let me try it this way. Age. Here we go. Age. Yeah, age group. I'm pretty sure I saw one for age. Well, I'd have to look through this a little bit more carefully. What I'll do is, with this new version of the database, I'll go through there and I'll see if I can isolate some specific variables that I think are going to be important to you. You can do this on your own as well, and you can pick through them. Okay, so let me just see the people online if they have a pretty good idea of what we're going to start with in terms of evaluating these variables. Let me find these guys. Where'd they go? There they go. Okay, so you guys got an idea of what you want to do with this database. It's a little tedious because there's so many variables and so many variables you're not going to wind up using. So select your topic, then go through that list of 185 variables and decide on what things might be relevant to what you want to investigate. Yes? Well, on the demographics, for instance, if one of the variables that you're looking at is whether or not they're insured, then you might want to look at that in terms of what percentage of people are insured in general, right? And then you also might want to look at it from the perspective of is there a difference between the number of males that are insured versus females that are insured? Does the income level have something to do with whether or not you're insured? In other words, a little bit of an idea about your variables, what your demographics for your population that you're examining is. And then eventually what you're going to wind up doing is seeing if there's a relationship between having insurance and getting a flu shot. In other words, are you statistically more likely to get a flu shot if you have insurance, or if you're female or male, or if you have other health problems, and if you have diabetes, for instance. Okay, but we'll take a look at this in the beginning now. Just get a handle on the data, and choose your topic, get a handle on the data, and start to put together some descriptive statistics and a description of what you want to examine within that group of topics that we have. Okay? So we'll see. What I need for you guys is to take your own unique perspective, look at this, and then give me some feedback on what you want to do and which of these variables and data that you want to work with. Okay, so that way I can give you some feedback on it. Okay, so let me get this out of the way. Let me move on to our topic for today, which is analysis of variance. I think I'll keep this database open for now. And I'll tell you what, I want to see if I can't. Okay. Okay, let's see. I'm going to sort it by measure. Okay, so now all of my scalar variables are down here. And I'm going to take a look at, let's see, total number of minutes, number of days consumed, last 30 days. Total ounces, cost of. I'm going to pick one of these variables. Let's take this variable, total minutes sitting on an average day in the last 7 days. Okay, that's a variable that might be of interest to us. It's sedentary, might be a measure of a sedentary lifestyle. And I'm going to go back to the data view, and I'm going to be taking a look at that variable. It's all the way down here now. Okay, so in that variable, tell you what, let's do something even a little bit more drastic here. Let's narrow this down so I don't spend all day running through this. Okay, I'm going to get rid of these other variables. Okay, and what do I want to relate it to? How about have you been told by a doctor or nurse that you have depression? Okay, so I'm gonna look at that one variable. I'm going to get rid of everything else. That's a nominal variable, right? Because that's a yes or a no. And maybe I'm interested in seeing if there's a relationship between the average number of sedentary minutes per day and whether or not a person has been told by a doctor that they have depression. Okay, so now I have to code this variable, told that you have depression. So let me go to the code book and see what the okay, have you been to code? So 1 is yes and 2 is no. So I'm going to go in here and I'm going to code that variable. 1 is yes, and 2 is no. And I'm going to say OK. So now I'm going to go back here, and now I just have the two variables to work with. Okay, so let's see, what's the average number of minutes that a person spends sitting within this group of New York City adults 18 and older? So analyze, descriptive statistics. If I'm dealing with all of the adults, I can just go over to descriptives and say I want to know what the average, standard deviation, so on and so forth is for total minutes. I'll click OK. Okay, so now let's see what I wound up with here. I wound up with an average of where is it? Where is the average? Here it is, almost 400 minutes, 397 minutes. Well, let's see. What do I know? How many people in New York City have been told that they, by a doctor, that they have depression? So I'm going to go into analyze, and this time that's a categorical variable. So I'm going to look at frequencies. And I'm going to ask it to tell me some information about that variable. And maybe I'll go into charts and ask it to give me a pie chart as well. Okay, so let's see what the distribution of depression is in New York City. Well, as it happens, it looks like 14.9% at some point have been told by a doctor that you have depression. Okay, so, and we can see what we can illustrate that with a pie chart, the percentage of the population that's been told they have depression. Okay, so now, let's say that we want to examine whether or not a person that's been told that they have depression is more likely to have a sedentary lifestyle. So let's take a look at that. Analyze, descriptive statistics. This time I'm going to go to explore because I don't want to look at just one block of data, which is all of the people that have been and the number of minutes that they spend sitting, but I want to break it up, factored into two groups. One that has been told that they have depression, one that hasn't been told that they've ever had it. So I'm going to go to explore instead. And this time I'm going to put my numerical variable, total minutes, into the dependence list. And have you ever been told that you have depression, into the factors list? I'm going to ask for it to give me a 95% confidence interval. I'm going to also ask for it to plot a histogram for us as well. Okay. So let's go ahead and do this analysis and see what we get. Okay, let's see what we got here. Okay, I'm going to open this up a bit. So what we've got is the mean is for people who have that have been told they have had depression is 426 minutes that they spend sitting a day. The mean for people that haven't been told they have depression is 392 minutes. Does that suggests that people that are depressed tend to be less active? Does that really prove that though? We got two problems with that, right? There might be something else going on here. Someone's ill, they might be depressed. Might have been told they're depressed because they're ill. So maybe it's got more to do with the illness than the depression. So that's one issue. The other issue is that we see that there's a difference in the averages, but that this difference may be due to chance. It may not be statistically significant. How do we test? When we have two variables, when we have a numerical variable, categorical variable with two values, how do we test whether the two means are different? T-test, right? So let's do a t-test. Analyze, compare means, independent samples t-test, two independent groups. I'm going to put the test variable, total minutes, in here. I'm going to put ever been told you're depressed. And I'm going to click it's 95%, I guess, right? Yep, as before. And I have to define the groups. And I have to tell it what the values were that represent yes and no, and it was 1 and 2. Yep. And in fact, we don't even have to be concerned with the 3 and the 4 here because it's irrelevant. It's not going to analyze those anyway. So I'm going to click OK. Let's see what we wind up getting. Well, we get a bar plot, and the bar plot, it really, the median doesn't look all that different. The range doesn't look all that different. But let's see what we get in terms of like actual statistical significance. Okay, so the t-test, first of all, number one, Levine's test for equality of variances, right? Well, we look at this and we say to ourselves, if this significance for this box here is less than 0.05, we reject the hypothesis that the variances are equal, and we accept the alternative. So we use, in this case, we're going to use the bottom line. And the bottom line tells us the t-score, number of standard errors apart that these are, is 4.665, right? And the probability of getting this result, getting a t-score that big, these two means that far apart, in this size sample and in this population with this variability, is less than 0.1%. So if our null hypothesis was that there's no difference in the average number of minutes seating based on whether a person's depressed or not, and our alternative is there is a difference, we would reject our null hypothesis. Very neat. We've done this 1,000 times before. Maybe not 1,000. We've done this at least 10 times before. Okay. So now I'm going to take a different variable. And now I'm going to regret the fact that I eliminated all of those variables because now I need one of them back. And to do that, I'm going to just simply reopen. Can I undo here? Maybe I can undo. Oh, I got them back. What do you know? Okay, now this time I'm going to take a different variable. And I'm going to look for something like, let's see, education status, right? I'm going to take a look at that variable, and let's see it in the data view, education stat. Well, I'm going to look at it in the code book. Here's my code book, education status. Okay, let's see if I can't find up. Well, here's a variable called education. What is your highest grade or year of school that you completed? Less than high school grad, some college grad, and so we got 1 through 4 is the relevant data for us, right? So I'm going to compare that education level with whether a person was sedentary or not. Okay, number of minutes seated. So let's see if I can't find that education variable here. And what section is it in? How far down am I here? Let me see if I can't find it this way. And whoops. Escape. Go to variables. Oh, there it is right there. Education. Okay, so there's education. I'm going to get rid of these other variables. Just to make things simpler again. You don't have to do this. I'm just doing it because I want to make it clear which variables we're actually working on. Okay, so whoops. Okay, so now we are going to compare minutes sitting per day, in other words, sedentary lifestyle, which is a numerical variable. We're going to look at that from the perspective of level of education. Okay, so now how many categories do we have for education? Let's go in here and fill them in. We have one is high school, right? I don't remember exactly what they were. I'm going to make it up as I go along. 2 is some college. Okay. 3 is college graduate. Oops, graduate. Okay, I'm going to add that. 4 is big shot MPH. That's that. Okay, so we'll put that in there. Okay, so let's see what the relative amount of activity. Now, I have a numerical variable, so I'm going to find an average for that numerical variable, and I want to compare the averages, right? So I want to compare the average, go back to data view, I want to compare the averages of, say, college graduates, just simple college graduates, to high school graduates, let's say. But I also want to compare people who have some college to big shot MPHs, or I want to compare high school graduates to somebody that's graduated college. I have a number of different ways I can compare this. I have 4 different categories. So I have to run. Group 1, like high school against some college, and high school. I got to do t-test high school against some college, high school against college graduate, high school against graduate school. Right. So I have 3 tests right there. But then I also have to do, well, let's see, I have to do some college versus college graduate, some college versus graduate student. and so on and so forth. So I have to do the t-test 6 times to compare all these groups. Now, every time I do the t-test and use a standard type 1 error level, 0.05, what's the probability of my getting that wrong if I reject the null hypothesis? 0.05, right? 5%. So if I do it 6 times, right, it's like Russian roulette. You know, you put one bullet in there and you spin it. Eventually, it's going to go off, right? Because we're repeating the test over and over again. So there's 2 issues with using the t-test when we have multiple values for that categorical variable. One is by repeating it, we increase our chances of being wrong. The second is that it's tedious. We might have, if we were looking at ethnicity, there might be 10 ethnic groups there. So we wouldn't want to have to do the test 10 times 10 times 9 times 8, whatever number factorial that is, that's going to be the number of combinations that you can get. We need a mechanism to do basically a t-test, but to do it with multiple values of the variable, of the categorical variable at once. And that is analysis of variance. Okay, so I'm going to do an analysis of variance on this. Okay, and then after we've done analysis of variance on this real data, I'm going to do a demonstration of what we really did with really small numbers and small groups, so we can see how this actually does work. Okay, so I'm going to go in here and I'm going to say analyze. Well, let's see. It still is. Let's see. Analyze. Oops. You know, funny thing about SPSS. If I don't have the data file, if I don't have it, I do have the data file up front. Descriptive statistics. Compare means. Why is it not showing me all the possibilities here? Analyze. Descriptive statistics. Means. Why is it not showing me all the possibilities? Why is it not showing me? I'm not making this up. We saw that before, right? There was more stuff. Maybe I need to have the output table open here. Here we go. Don't ask me why that's happening now. I have to have the output table up front in order for me give me all the different options. That's a bug. Don't worry about that. Hopefully it doesn't do that in your version. If it does, you know to like it here. You know that if you have that table in front, it doesn't. If you have the data view in front, it doesn't give you all of the options that you need. That you have to have the output window in front. So again, that's just a bug. It's not anything we're doing. So since I'm still comparing means, I'm not doing a t-test. I'm doing analysis of variance, but that is still comparing means of one group versus another group. So I'm going to go to one-way analysis of variance. Don't worry about one way. It means that we're involving only one categorical variable. So I'm going to go one-way analysis of variance, and it's going to come up with a with a dependence list, just like before. I'm going to move in total minutes. It's going to come up with educational status. I'm going to move that into factors. Okay, so now it doesn't ask me to define the variables, to define the numbers, 1, 1, and 2, because it's going to do it for all of the values that are in there, 1, 2, 3, and 4. So for right now, I'm not going to worry about these options that we have. There's one called post hoc, which is important to us. We're going to be getting to that in a second. Okay, but I'm just going to click OK. Okay, and it's going to perform an analysis of variance. Let's see what our output table looks like. Oops. I think that's our output table here. I'm going to do it again so I can scroll up, make it easier for us to see here on the screen. Okay. Okay, let's see. Okay, here's our analysis of variance. It comes up with a statistic that's called F. And that statistic has a value, a number. It turns out that it's 253. And the probability of getting that statistic, given that getting that statistic by chance, when there isn't a difference between the means of the populations, in other words, incorrectly rejecting the null hypothesis, the probability of doing that is well below 0.05, right? So this means I can read my original null hypothesis is that there's no difference between the 4 educational levels and the number of minutes they spend sitting. Okay. Now our alternative hypothesis is that there is a difference. but that difference could be between any of the groups. So the analysis of variance doesn't tell us which groups are different. It just tells us at least one of the two of the groups are different from one another statistically. Now we have a task where we have to figure out which ones are different. If we hadn't got a value for the significance of less than 0.05, that would have meant that we can't reject the null hypothesis, and we don't have enough evidence to prove that any of them are different. So we'd be done. We'd stop right there. Now we know that at least two of them have different averages from one another, but we just don't know which ones to compare, right? So now, you remember we went up there and we took a quick look up here, and there was something when we went into compare means and one-way analysis of variance, there was an option over here called post hoc. Anybody knows what post hoc means in Latin? It means after the fact, right? So post hoc means after we've made our analysis and we've determined that there's a difference, we can click in here and we can say to ourselves, let's do a post hoc test, a test that'll help us distinguish which ones are different from one another. There's a number of different ways to do this. For today's session, we're not going to be too concerned about how they differ. Typically, in these classes before, we've either used a technique called Bonferroni or a technique called Tukey. They're named after the people that developed them, and they're going to help us determine whether or not there is a difference. I'm going to use Bonferroni first, and we'll run it again, see if we get a different result with the other. Most likely, we won't get a different result. So I'm going to click Continue, and I'm going to click OK, and it'll run this analysis again, except this time, it will do an analysis do post hoc analysis too. And in the post hoc analysis, what happens is, oops, I'm trying to grab that corner there a second. I'm going to let me redo this so that I can scroll up. Okay. Okay, good. So now in this analysis, it actually compares high school versus some college, high school versus college graduate, high school versus MPH, some college versus high school, some college versus, it does all of the different permutations, all of the different combinations. And if I look over here, I can see my significance, my probability of getting that result by chance, that there's a difference between each one of these groups. And nobody's more surprised than I am by this outcome. What does it tell you? They're all different. They're all different. Just a caution, I want to show you that high school versus some college, when you go down here to some college, it repeats that analysis, high school and some college. So it actually runs all the analyses twice. But you don't have to worry about that because the results will always come out the same. So that's pretty interesting, right? That there is a difference. Let's actually, now that we found that difference, I'm curious to see let's go in here, analyze. This is why you do your descriptive statistics first, right? Because I'm surprised at that result. Maybe I shouldn't have been that surprised. Let's go to Explore. Let's go to total minutes. Let's look at it by educational status. And let's ask SPSS to show us what the difference is here. Okay, and let's see what the averages look like. Okay, high school, 287 minutes. Some college, 353 minutes. College graduates, 413 minutes. Big shot MPH. Boy, you guys are spending a lot of times on your butts when you get your graduate school degree. And not only even just looking at this, we see a big difference here, even before we run any statistical tests, right? And not only that, but the difference is consistent. The higher, each time you go to a higher level of education, you get a more sedentary lifestyle. Boy, that's interesting, right? Maybe we should add that to one of the options, right? It's pretty interesting, right? Did you know that there's such a clear association between educational level and sedentary lifestyle? Maybe that's something one of you want to do. A couple of you, remember, you're going to wind up doing, a lot of you people are going to wind up doing the same thing just by the nature of the beast. But I did not expect that result or that dramatic a result. So we use descriptive statistics to show us the differences between these groups. We can see if the results are normally distributed. Oh boy, we get some people that maybe these people are disabled. they can't move. You're right. There might be a reason why it's skewed slightly, but it's fairly normal, these distributions. Let's look at the post hoc tests. Well, look at that. Look at the medians, right? Just go up and up and up and up based on educational level. Very interesting, right? Right? So maybe that's an option. So what did we just do here? If we were doing a project, right, we would have started by researching a little bit, introduced it with what we were looking for and what we expected to find, maybe done a little bit of research and found a couple of articles that discuss education level and sedentary lifestyle and bring up what they've mentioned previously. Then present the descriptive statistics, the populations, and how they're distributed, and so on and so forth, and then do our statistical analysis of variance, and then have our discussion and conclusions. Right? So pretty straightforward way of doing this thing. So this is maybe I will add this as another option. So if you guys want to do it, you can do it. Okay, you guys online, are you surprised by that? Let me ask you, are you seated right now? No, is anyone standing and listening to this by any chance? I was actually talking to someone that I was having a little bit of a conference with, and he was working at a standing desk as we were talking, right? And it was a little bit freaky because normally I go and visit people, we sit down, we have a discussion, we have our paper and stuff like that. It was a little odd, like having a conference with someone that was standing up at a monitor. Yeah. Okay. So yes, I'm surprised by this result, and I think if you guys play around with this data set, you may find other things that are surprising like this. So I encourage you to go ahead in there and play with this material, and we'll wind up with some more interesting projects. Okay. Like I said, since I'm gonna be putting up this new data set, I'm gonna also give you some previous projects you can actually look at and see how those people had done it before. Okay, they will have worked with a different data set than you, so I'll know if you used a different data set. Okay, so at any rate, okay, now I want to demonstrate to you what this analysis of variance is all about. Okay, and one of the ways that I'm going to demonstrate to you, I'm going to play a video. You might have watched this video before, and it gives you an idea of kind of what we're doing here, and then I'll do a bit of a demonstration. The video may be a little choppy from the broadcast, but sometimes it works. Sometimes this works out okay. Sometimes not. If it is choppy, you can kind of play it in the background from the same link that I'm going to start it from. Okay, and this is it's going to be in the class sessions. And it's going to be in this session. And it's going to be this little video right here. This week, we're going to use analysis of variance to compare means again, except this time we're going to be looking at 3 or more groups. This past spring, I was lucky enough to get to the Brooklyn Botanical Gardens while the cherry blossoms were in bloom. And I noticed something very interesting. They filled an entire field with these beautiful cherry trees. And there were just so many of them, and they were so close together that it was hard to distinguish the blossoms from one tree from the blossoms from another tree. There were a variety of trees that were present at the Brooklyn Botanical Gardens. Some of the trees were wide and very full of blossoms. Others of the trees were much narrower. And I noticed that if the trees were very wide, if the blossoms were really spread out, that in order to be able to distinguish between individual trees, the tree trunks had to be very far apart. On the other hand, if the trees were very narrow, the trunks didn't have to be that far apart in order to distinguish between individual trees. I further noticed that the trees were symmetrical. The trunks were in the middle of the trees, and more of the blossoms were towards the center of the tree, fewer were far away from the tree. I realized that there's something else that has those same characteristics. I look at the normal distribution. It's bell-shaped so that the center is in the middle of the distribution. And more of the values are close to the mean, fewer are further away from the mean, and it's symmetrical. Here, we see three groups represented on the top and on the bottom. The variability is the same for all of these groups. On top, the means are close together, so it's hard to distinguish between the three groups. On the bottom, the means are further apart, making it easier to distinguish between them. Here, the means are the same, but the variability for the groups on the bottom is much smaller. So, even though the means are the same, we can distinguish easily between the three groups in the bottom set. Let's create a new statistic that we're going to call F. F is going to be the ratio of two numbers. On top, the numerator is going to be the variance between the means in several groups. The larger the variance between the means of the groups, in other words, the further apart the means are, the larger that ratio F is going to be. On the bottom of this ratio, we're going to put a number that represents the variance within the groups. As the variability within the groups becomes smaller and they become narrower, F also becomes larger. Smaller number on the bottom makes it a bigger number. Our statistic F represents a ratio of the variance of the means over a number representing the variance within the individual groups. The further apart the means are, and the narrower the groups are, the easier it is to distinguish between the groups and the larger the value of F. F has a probability distribution associated with it. In this graph, we can see that there's a region that if F is large enough, we can be safe in saying that the means of the groups are different rather than being from the same population. Our lab exercises this week, we're going to use the F statistic to determine when we can distinguish between means of three or more groups. In this chapter, you'll find a demonstration of using Excel to calculate the F statistic or analysis. We're going to give that a try. You'll also find a demonstration of using Spss to do the same. Okay, so there's on Blackboard, there is a small data set. There's two versions of it, an Excel version and an SPSS version. Were you guys able to see and hear that online, by the way? Are you guys still awake there? You know, I can't tell. Sometimes there's a little bit of a lag, so I don't know if it's them or me. Okay, I think that was a yes. Okay, all right, good. I'm going to open up a data file that's that I downloaded from our demonstrations for our demonstration. It's on Blackboard right now. Let me just see if I can't find the right folder for it. Actually, I think it's out here. I'll move some things around here. Should be in here, I think. Okay, yeah, here we go. Okay, I think this will be the file. There's a version of it that's completed as well. So now I'm going to demonstrate actually doing this calculation. So let's say I have three groups, and I take three samples from three different populations. I want to demonstrate that the mean of those three groups, at least two of those three groups, is different, or I want to know if they're different statistically. Okay, so my null hypothesis is going to be that the mean for population A is equal to the mean for population B is equal to the mean for population C. That's a typical null hypothesis for analysis of variance. My alternative hypothesis is that at least two of the means are different. They don't all have to be different. A could be different from C, B could be different from A. Don't all have to be different, but at least two of them are different, right? Not all of them are the same. So with that, on that basis, I'm going to actually do the calculation now to compare the variability within the samples themselves and between the means of the samples. So I'm going to take sample A, right? I'm going to go over here and I'll copy that, and I'm going to paste it down here. And I'm going to find the mean for sample A. Okay, and here's the mean for sample A. Okay, I'm going to do the same thing for sample B. Okay, and here we copy this. And I'll find the average. Now we know the means are never going to be exactly the same. The question is, are they different enough for us to be 95% certain that the population means are different? That's really what we're after. Okay, so right off the bat, I'm starting to see some differences in the means for these samples from these three groups, these three different groups. But the question is, with these small samples, is that difference big enough for us to say that we would only get this difference, this big a difference, by chance, less than 5% of the time? Okay, so there is our means for each one of the groups. Now, I'm going to go ahead. Remember at the beginning of the semester, we calculated the squares of the differences from the means for each, in order to figure out the variability, standard deviation, and variance. I'm going to actually repeat what we did at the beginning of the semester. So the average is equal to this value, and I'm going to make it a fixed box here by putting in the $2 as we learned earlier. Okay, and I'm going to copy that down, so it's going to be just 1.8. Okay, so we just repeated that. I could also just type in 3.4 and copy it down. That'll work too. Okay, oh, wrong one. Edit, fill down. And this one was 4.4. For our purposes, this will work well enough for now. Actually, I can do it the other way, just so you see each way demonstrated. Okay, so now what's the difference between each value and the mean? Okay, well, it's going to be equal to 3 minus the mean, and hit enter. And then I'm going to copy that function, that calculation down, so I get each one of the differences. Equals 5 minus 3.4, and copy that down. And finally, I'm going to do this last one, 6 minus 4.4, then do that for each other value. We know if I just add them up, they add up to 0. So in order to avoid that, I have to square them. So this location is going to be equal to this times itself. So that's the square of the differences between the mean and that value. And I'm going to drag this down. Okay, this is a repeat of what we did before, so it shouldn't be anything really shocking. Okay, and square the differences. Okay, I'll copy that down. And now I'm going to add up all of these squared differences. And we know we call that the sum of the squares of the differences, or sum of squares equals sum of all of these numbers. Whoops. Try that again. Okay, that's the sum of the squares for each one of these different values. So this is a measure of the variability within each group. That's a measure of variability within the groups, right? Not between the groups, but within the groups, because it's looking at the differences between each one of their means and each value within the group. So, okay, so now let's see. I already had set up here for this to carry over the sum of the squares of the differences within. In other words, if we add all of these together, 2.8, 5.2, 17.5, it becomes 25.2. You can see those three cells are added up together. Now, what is the degrees of freedom that we're going to assign here for this calculation? Well, the degrees of freedom is going to be equal to there's 5 people in each group, right? And there is, let's see, there's 5 people in each group. It's the number of subjects minus the number of groups. How many subjects do we have? We have 5 in each, so we have 15 minus 3. So the degrees of freedom are equal to 12. So what we wind up with, if we divide 12 into 25.2 degrees of freedom, that's like dividing n minus 1 into the variance to get the into these sum of squares, get the variance as we did before. We get a number, the mean sum of the average sum of squares within the groups is equal to 2.1. And that average sum of squares, that mean sum of squares within, that's our denominator. That's our measure of the variability within the groups. Now we need the top part of that fraction. We need the variability between the groups, which is the variability between mean 1 and mean 2 and mean 3. And okay, so the way we're going to do that is, let's see where that's located. So the overall mean of the means is 3.2. One mean is 1.8, one mean is 3.4, and one mean is 4.4. So the overall overall mean was 3.2. The difference between that mean and the overall mean is minus 1.4, and this is 0.02, and this is 1.2. We square those values for the differences of the squares of the differences between the overall mean and each individual mean, and this is our differences squared, right? So now we multiply by the number of values that are in each one of these, because we're interested. We could wind up with an uneven number of individuals in the different groups. We were lucky it was 5, 5, and 5, but it could have been 5, 4, and a 12 or something like that in one group, right? As it happens. So our differences squared, the total sums of the squared differences is equal to 17.2, and we carry that down here. Now, how many degrees of freedom are there between the means and the groups? Well, there's 3 groups, so we subtract the number of groups minus 1, so the number of degrees of freedom here are 2. So the value that we get for the mean sum of squares between the means as opposed to within the groups is equal to 8.6. So the number that goes on top here is 8.6. This is a measurement of how far apart the means are, and this is a measurement of how narrow the variability within each group is. So we want a big number here because we want the means far apart, and we want a small number here. And overall, it gives us a number 4.09. That's our value for our analysis of variance. We use the letter F to represent that. So now I have to go find a distribution that tells me whether that number is big enough to reject my null hypothesis. So I need to know that that number, getting that big a number, will occur less than 5% of the time by chance. And the rest of the time it'll occur because there really is a difference between at least 2 of the means. Okay, so now I need a distribution that will tell me whether that's that big a number. I need a critical value for F, the analysis of variance. So I'm going to go up here and I'm going to look for ANOVA table. Okay, or F table. Hopefully I can find it. Here we go. Did I find it? I don't know if I did. No, I didn't. Close. Gresty, maybe a Gresty. There it is. There is our table. And take a look at that. That looks very much like chi-square, right? It's kind of thing where we want to be as far to the right as possible, to the point where the number of possible outcomes that we would get are less than 5%, right? So we want F to be big enough that the right tail is less than 0.05. So now, how do we decide which one of, we have a whole table here, how do we decide what our critical value is? Well, this entire table assumes that we're looking for a right tail probability, an alpha error, of less than 0.05. But now we have to tell it, well, what are our degrees of freedom? Problem is now we have 2 degrees of freedom. We have 1 degree of freedom for the number of groups, and we have another degrees of freedom for the number of individuals in the groups, right? So we're not going to have, you can tell, we're not going to have an infinite number of groups. So you can pretty much tell that the horizontal row, actually they put it infinity anyway, but the top row represents the number of groups that you have. The number of degrees of freedom for groups, which was 3 minus 1 was 2. So we're going to be working in the second row. And the vertical row represents the degrees of freedom within the groups, which was the number of people, 15, minus the number of groups, which was 12. So we're going to look over here to 2 and 12, and our critical value for F, in order to get less than 5% chance of being wrong if we reject the null hypothesis, is 3.89. So that means when we go back here, have we exceeded our critical value? Yes, we have. Thus, we can reject. Thus, we can say is less than 5% chance of being wrong if we reject the null hypothesis, and we say we reject the null hypothesis and accept the alternative hypothesis. The only thing that this doesn't do for you is what? Doesn't tell you which groups are different. Exactly right. It doesn't tell you which groups are different. That's what you need the post-hoc test for. Now, in real life, unless you lose your minds, you're not going to do it this way. You're going to use SPSS to do it. And in fact, we have a copy of a file that duplicates this, I believe. I hope. And I'm going to, it might be the other one. Let me see. I hope I opened the right one. I hope it opens. I hope I opened the right one. I hope SPSS was working. I have a lot of hope. Maybe I should open it from SPSS. We won't wait as long. Oh, no, there it goes. Oh, you know what it's doing?
7 o'clock.
It's actually opening up another copy of SPSS. That's interesting. Boy, every time I run SPSS on this computer, it gets stranger and stranger. Okay, so here's our three groups. Here's A, the values for A. Here's the values for B. Here's the values for group C. Okay, and here's our variable view where it's coded by A, B, and C, and so on. So now I'm going to go in here. I'm going to analyze descriptive statistics. I'm just, for the hell of it, I'm going to say explore. And I'm going to say, tell me about these three groups. Well, first of all, number one, I have to change something first. Okay, in the variable view. It thinks that the variable measurement is a nominal variable. It's actually a scalar variable. It's actually a number. And the reason why it thought that was because it sees that I made the numbers really small. So it thinks it's a categorical variable. It just made the assumption that if the numbers are coming up small like that, it's probably categorical, right? So it made that assumption incorrectly. They're numbers as far as I'm concerned. Okay, so now I'm going to go into Analyze, Descriptive Statistics, Explore, and I'm going to ask SPSS to calculate the average measurements for each one of these groups. Okay, and let's see what we wind up getting. We get for group A, we get 1.8, as we saw before. For group B, we get 3.4, and for group C, we get 4.4. So we see that the average for each group is different. Now, the biggest difference is between C and A, so I think that's a pretty good candidate for probably being statistically significant. 3.4 versus 1.8, that's pretty different too, but 4.4 and 3.4 are a little bit closer. It's hard to tell. Right? We really need to do a calculation to determine this. And that's where our analysis of variance comes in. Analyze, compare means, one-way analysis of variance. So my measurements go in here, my group goes in here, my grouping factor goes in here. And this time, well, I'm going to run my analysis of variance and see what my result is. Okay, and we already know from our analysis that, well, let's see, we have an F score of 4.095, just for the hell of it. Well, same one we got. So we must have done it right, right? That's gratifying, right? So what's the probability of getting that big a F score in analysis of variance if you're wrong about the null hypothesis being rejected? The probability is 4.4%, less than 5% chance of you being wrong if you reject the null hypothesis. Nice thing about SPSS is not only did it give us our value of F, which we could compare against the critical value if we wanted to, but we didn't even really need to because it gave us the actual probability of being wrong. So we know how close we are there as well. So we got that. Now I want to point out to you that actually what's in here is all of the values we calculated. The sum of squares between groups, 17.2, divided by 2 degrees of freedom is our 8.6, which was the top of the fraction. Our 25.2 divided by 12 degrees of freedom, 2.1 was the bottom of the fraction. And that's how that F score comes up. So if I left one of these numbers out, you could figure out what it was because you know how they're calculated now. So that's what this whole table summarizes. So now that we know that there's a difference between two of these groups, let's do our post-hoc test. So I'm going to go in here, I'm going to say Analyze, Compare Means, One-Way Analysis of Variance, and now I'm going to go into Post-Hoc Test, and I'm going to ask it to do the Bonferroni tests. And I'm going to click OK. Okay, so let's see which of these are statistically significant. A versus B, not significant. A versus C, that's a significant difference, right? But that's less than 0.05. B versus A, well, we just saw B versus A. It's going to come up to the same, 3.19, right? Nothing new there. And B versus C, that's a new analysis. That's also not statistically significant. So the only statistically significant difference here is A versus C, or C versus A, whichever way you want to look at it, right? So those are the only two means that, given this sample size, this amount of variability in the groups or between the means, that we could say for sure is statistically different. Okay, and that was 0.045. Okay, so now let's do the let's try a different post hoc test. Analyze, compare means, one-way analysis of variance, and this time as post hoc test, I'll try Tukey. See if I get the same result. Okay, and let's see. So for this result, we wind up with, it looks a little bit more dramatic. There's a different, it thinks that the probability of being wrong and rejecting a null hypothesis is 0.037, is 3.7% instead of 4.5%. So it thinks it's less likely that we'd be wrong if we reject a null hypothesis. So which of these two tests is the more conservative, does it sound like? Which one was closer to 0.05? The Bonferroni. So that appears to be more conservative, because in order for you to reject the null hypothesis, Bonferroni is more rigorous. It makes you do more to prove it. Tukey was willing to say that, gee, look, gave you a much smaller probability of being wrong. So it's easier to satisfy to reject the null hypothesis. So Bonferroni is a more conservative test. You know, if you're concerned about that, you might use that. If you just want to look good, make sure you can reject the null hypothesis, I guess use Tukey. But you got about 11 other choices in here. You can pick and choose which one you want. There in reality, there's reasons why you choose one over another in different situations. It's a little bit outside of what we really need to know for this right now, especially in terms of what we're going to be doing with the our projects. Now, the interesting thing about this is there are not a lot of scalar variables, as we saw in the data set for SPSS, right? That for the community health survey. Let me just go back there and see if I'll open up a fresh version of it. Okay. I know it can't be open because it's already open. Thanks for nothing. Okay. Let me go here to SPSS, and I will close this one. Yes, I want to proceed. No. Okay. Any others open here? SPSS. Output. There's another data set here. I can't close that one. Okay, let's say open. Data. Desktop. And let me see, community health survey is going to be, the original community health survey is going to be here. Okay, let's see what we have here. And we have, okay, so now one of the things I can do is go in my variable view, and I can ask SPSS to sort this data file. Now remember, it makes a quick judgment on its own. What's a nominal variable? What's a scalar variable? If it sees values like 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, it assumes that they're categorical variables. Just makes that assumption without any proof, but only that's the way it's set up to do this. If it sees numbers that are like 137, 152.1, it calls it a scalar variable. Again, it makes a judgment about that stuff. So what I want to do right now is I want to sort this data. I'm going to sort the variables, and I want to sort them by the type of measure that it is. And I want to do it descending, because what it's going to do is it's going to do it alphabetically. So if I do ascending, it's going to put the nominal variable ahead of the scalar variable and ahead of S. If I do it the other way, I'll put the scalar variable, which is what I'm interested in. I want that on top. And sure enough, there it goes. It sorts it. Okay, let's see what scalar variables. We have some, right? We have, during the past 30 days, what number of drinks have you had? I presume alcoholic drinks. Number of alcoholic drinks, number of minutes sitting, number of sodas, number of sweetened drinks, number of ounces of that stuff, cost of 20 cigarettes, cost how much you pay for a pack of cigarettes, ounces of soda, BMI, body mass index. So if it's got body mass index, it must have weight and here you go, survey weight, and it must have height also buried in here somewhere, because otherwise they wouldn't be able to calculate the BMI, right? So survey weight, survey year, unique identifier. I suspect that there's some that we're missing here because they're miscoded as well. Here's survey weight and BMI. Maybe they don't bother to record the height because they can deduce it from either one of those two. Okay, so if you want to do an analysis of BMI related to some other variable here, you have the numerical data. If you want to do survey weight is not a person's weight. Survey weight is most likely, if you look that up in the code book, survey weight may have something to do with weighting the data in order to make it less how should I put this? Less compromised by things like the distribution of ages in the population or something like that. It may be a correction factor for the data that's used in some of their other publications. So I wouldn't use that as a person's weight necessarily. But body mass index, if you have that for each individual, you have a number of other numerical variables. It's nice to have a numerical variables because then you can do descriptive statistics that involve mean, standard deviation, variability. You can do t-tests, you can do analysis of variance, and so on and so forth. But the bulk of the data is what kind of data? The bulk of the data is categorical and nominal data. And with categorical and nominal data, what kind of analyses do we do instead? We do chi-square, relative risk and odds ratio. Just a quick demonstration of a couple of those. Okay, so now, have you had a colonoscopy in the last 10 years? And had an HIV test in the past 12 months. Let's see if there's an association. Okay, I'm going to get rid of all of these for now. You don't have to do this. I'm just doing it because it makes it a lot clearer what we're doing. And I'm just picking two nominal variables out. Okay, there's two nominal. I know these are two nominal variables. I don't know what the values are, but I'm going to take a wild guess and say one is yes and two is no. Right? That doesn't sound like too hazardous a guess. You'd actually look it up in the code book to make sure. So I'm going to put in here whoops. Excuse me. Cancel values. Okay, one is yes for HIV test, and two is no. I click OK, and over here for colonoscopy, I'll say one is yes, and two is no. Okay, so I'm going to go back to the data view. And what do you think? Do you think there's an association between having an HIV test in the last 12 months and having a colonoscopy? You think if a person has an HIV test in the last 12 months, that they're more likely to have a colonoscopy also in the same year? I mean, it's a silly comparison, but I'm just throwing this out because I happen to have these two categorical variables that are yeses and nos. Think no, right? We're saying no. Okay, let's examine that. What is our null hypothesis? Our null hypothesis is that there's no association between being tested for HIV and having a colonoscopy in the last 5 years, whatever it says, right? Okay, so That's my null hypothesis. My alternative hypothesis is there is an association. Now, since it's a categorical variable, yes and no in each case, we choose one as the exposure. I'll call it HIV the exposure. I'll put it in the rows, and I'll put the colonoscopy into the columns. In other words, if you have an HIV test, are you likely to have a colonoscopy also? Okay, so I'm going to go in here, and I'm going to first, what kind of analysis are we doing here? We're doing a chi-square analysis. We're building a contingency table. So I'm going to go into Analyze. I'm going to go into Descriptive Statistics. And because we're first, before we do anything else, we got to build our contingency table, go into crosstabs. So now I'm going to move HIV test, yes or no, into rows, and colonoscopy, yes or no, into columns. And I'm going to, there's a number of ways I could view this. I could say to myself, well, someone's getting an HIV test probably younger, so they're less likely to have a colonoscopy. Someone's getting an HIV test, maybe has health problems, maybe it's more likely to get colonoscopy. So let's see what we actually see here. Okay, so I'm going to first, before I do anything else, I'm not going to do a chi-square yet. First, I'm just going to look at the data, the observed values. I'm going to make a 2x2 table. Okay, and here's our 2x2 table. Okay, how did it look? Let's see. 1,100 people in this survey out of 4,900 people that answered. A lot of people didn't answer the survey. 1,100 people said they had an HIV test, and 3,700 said they didn't have an HIV test over the past 12 months. That seems like a large percentage, right? Doesn't it? Maybe insurance requires it nowadays. I'm not sure, but that seems like a relatively, for just the general population, seems like a large percentage. So how many of these people, the 1,131, had a colonoscopy, had an HIV test, also had a colonoscopy? So it's 683 out of 1,100. So almost 70% had a colonoscopy over a period of, and this is only at, oh, you know why the sample's so small? It's only adults over 45 years old. Well, that kind of, that changes my view of this thing a little bit. Okay, so what about people that didn't have an HIV test? Well, it's 24 over 3769. It's still more than 50%. So maybe there isn't a difference here. Maybe there is. What's the overall prevalence for a colonoscopy? Well, of people of adults over 45 years, 3,100 out of 4,900 that responded had a colonoscopy. 75% of them. Interesting, right? This goes to show you, that it's one of those diagnostic tests that's being very widely used. Okay, so at least in that age range. Okay, so let's take a look at this. I want to look at this percentage by. I'm going to look at this as percentage by rows now. So analyze, descriptive statistics crosstabs. And this time I'm going to go into cells and ask it to show me the percentages by rows. And I'll click OK. Okay, let's see what this looks like now. Well, for the people that had HIV tests, 60% had colonoscopies. And for the people that didn't have HIV tests, 64% had colonoscopies. So a greater percentage that didn't have HIV tests had colonoscopies than did have colonoscopies. Well, how do I determine what the risk ratio, odds ratio, whether or not this is a statistically significant difference? Well, the way that we do that is we actually do a chi-square analysis, and we actually calculate odds ratio and relative risk. Excuse me. I'm going to go up to Analyze, Descriptive Statistics, crosstabs. I'm going to go into cells. I'm going to turn off the, I could have also calculated expected values as well. I'm going to turn that off so it doesn't clutter the table too much. I'm going to go into statistics and tell it to calculate chi-square and calculate risk, or odds ratio, in other words. Click continue, and I'll click OK. And we just did this on our exam, didn't we? So here is our crosstabs table. Let's see if there's a difference. Well, the Pearson's chi-square value is 5.7. 1 degree of freedom. Why is it 1 degree of freedom? 2 rows, 2 columns. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. Right? So what's our probability of being wrong if we reject the null hypothesis that there's no association? It's less than 1%. Right? So I would reject the null hypothesis, say there is an association. between whether or not you have an HIV test. And let's take a look at the odds ratio and the relative risk. Okay, so if I look at the risk estimates, the odds ratio is 0.846. In other words, you're only at 84% as likely to get a colonoscopy if you had an HIV test as if you didn't, right? So, and what's the confidence interval for this? 0.739 to 9.7. What do we not see in that confidence interval? The number 1, so we know we can still reject the null hypothesis. And the relative risk is 0.939, and that's 0.89 to 0.99. So a little closer call there, but it still doesn't include 1, so we reject the null hypothesis. Now, this is interesting. It seems like there is a slightly lower risk, just look at risk rather than odds ratio, slightly lower risk of having a colonoscopy than if you have an HIV test than if you don't, right? It's actually, if you look at the numbers, the rates at which these two occur are not very different, right? This is an example of a result that, while it's statistically significant, clinically, you say to yourself, it really doesn't look like there's that big a difference. So it may be a statistically significant result, but not really be a very clinically significant result. Really, probably does. It looks like there's really not much of a difference there's really not much of an association clinically versus statistically. One of the reasons why we got a statistically significant result is because the sample size is so large. Imagine this. Imagine that you had two populations you wanted to compare, and you want to see if the average blood pressure of this population was equal to the average blood pressure of this population, right? If you sampled every person except one in each population and said that was my sample, right? Those two numbers would be different, right? So your sample size is so large that it's easy to prove that they're statistically different but I mean, clinically, they might be only a tenth of a millimeter of mercury different, something like that. So you can have situations where, because you're working with very large sample sizes, that you can get a statistically significant result. But when you examine the real differences between the two groups, it's not clinically significant. It really doesn't make any difference what level they're at in real life. Okay, so what do we do tonight? We learned a new method to deal with numerical variables when we have multiple values for the category we're dividing them up into. Where might that be useful? It might be useful for different education groups. It might be useful for analyzing a numerical variable or an averages based on ethnic groups. And there are ethnicities in here. It might be useful for different age groups and so on. So we found that a useful way of comparing those averages and numerical variables. We also looked at the data set that we're going to be working with. We looked at how to manipulate it a little bit, and how to code it if we need to add some coding to it. We have a copy of a code book. We have a copy of the data set. So from now on, as you guys are working here at home, use the 2014 code book and code set rather than the 2013 one. If you've already started doing a lot of work on the 2011, you can let me know, and I'll put it. I'll email it to you. You can use it you can continue to use it. But I'd rather we use the more recent one. Okay, so that way you guys are kind of like doing your own work. You don't have to. You're not going to wind up duplicating the last semester's work. Give me a chance to put up a couple of examples of their work as well, so you can see what they did. Okay, so I'm going to stop there. And if you guys got questions on this, one other thing. I really shouldn't do this right after a test. The instructor evaluations are open. I'll give you the range of dates or something like that. You can go onto your portal site, and there's a way I'll post an announcement on Blackboard, but there's a route through your portal site to get to instructor evaluations. You do them on their own. They're anonymous. You can do them. There's a start date and an end date. Start date's, I think, about a week in already, and the end date is coming up. So I'll make sure you know what the end date is as well. But I'll post an announcement about that. So if you get a chance, please go on there the evaluations are really pretty valuable in terms of feedback, because then I know, for instance, I do my own surveys, but they're a little bit more detailed, and they're surveys that are put together a little bit more professionally. So it gives us an idea of what we're doing right, what we're not doing right. So it would help if you fill them out.